A retarder is a uniform plate of birefringent material whose optic axis lies in the plane of the plate. So what I have shown here is a birefringent material such as a calcite crystal whose optic axis is along the vertical direction. That is, it lies in the plane of the plate. A wave which is polarized at an angle theta with respect to the vertical direction is incident on such a plate. The thickness of the plate is taken to be d. When this wave is incident on the plate, on the first phase, it is split into two components, the extraordinary component and the ordinary component. At this phase, you can see that the phase difference between the extraordinary component and the ordinary component is equal to 0. As the vibrations move inside the crystal in the forward direction, the ordinary rays travels faster than the extraordinary waves. And because of that, there is a phase difference between the extraordinary and ordinary components inside the crystal. The phase difference between the waves will depend on the thickness of the plate, that is d. By suitably choosing the value of d, we can set the phase difference between the extraordinary and ordinary components that are coming out from the crystal to be pi by 2 or equal to pi. If the phase difference between the two waves is pi by 2, then they will combine to result in circular or elliptical polarization. In case if the phase difference between the two waves is pi, then we can see that when the waves combine, the polarization direction will be rotated by an angle 2 theta. That is, initially the electric wave was oriented like this, with an angle theta with vertical. Now it has been rotated by an angle 2 theta. So this is the new orientation of the electric field vector. The first type of retarder is known as a quarter wave plate. A quarter wave plate introduces a phase difference of pi by 2 and generates circular or elliptical polarization. The second case, where the plate introduces a path difference of lambda by 2 or a phase difference of pi, is known as a half wave plate. That is, a retarder is an optical device that introduces a phase retardation of one wave relative to the other, and the phase retardation will depend upon the thickness d of the plate. And these plates are generally used to produce circularly or elliptically polarized light and to analyze polarized light into its elliptical components. We shall dwell a little bit in detail to the design of a quarter wave plate. A quarter wave plate introduces a path difference of lambda by 4 or a phase difference of pi by 2 between the extraordinary ray and the ordinary ray propagating through it. Let us consider a wave vector E which is oriented at an angle theta with respect to horizontal. And this wave is allowed to fall onto the birefringent material. At the first phase, where the electric field vector is incident on the birefringent material, it is split into two components, the extraordinary component and the ordinary component. At d equal to 0, these two components are approximately having a phase difference of 0. As the vibrations propagate inside the crystal, the ordinary component travels faster than the extraordinary component, and the thickness of the crystal is so chosen that it introduces a path difference of lambda by 2 between the extraordinary and the ordinary components. So this path difference is equal to a phase difference of pi by 2. So as you can see, this is the ordinary wave and this is the extraordinary wave. And the phase difference between these two, this is equal to pi by 2. And these two polarizations combine to result in circular or elliptic polarization. Let us now derive an expression for the optical path difference and phase difference of a quarter wave plate. The optical path difference in the case of a quarter wave plate is NO minus NE multiplied by D. This has to be equal to lambda by 4. From this expression, we can get an expression for the thickness of the plate. This is equal to lambda divided by 4 multiplied by NO minus NE. The phase difference delta is equal to 2 pi over lambda multiplied by the path difference, and this has to be equal to pi by 2. A quarter wave plate is used for producing elliptically or circularly polarized light. It converts plane polarized light into elliptically or circularly polarized light depending upon the angle that the incident light vector makes with the optic axis of the quarter wave plate. That is this angle. We shall now discuss about the design of a half wave plate. A half wave plate is a thin plate of birefringent crystal having the optic axis parallel to its refracting faces, and its thickness is so chosen that it introduces a half wave path difference or a phase difference of pi between the extraordinary ray and the ordinary ray. We shall see in due course that a half wave plate rotates the plane of polarization of the incident plane polarized light through an angle 2 theta. That is, it inverts the handedness of elliptical or circular polarized light, changing right to left and vice versa. So let us see a typical case. As before, the electric field vector is oriented at an angle theta with respect to vertical. When it is incident on the half wave plate, it is split into ordinary and extraordinary components. At the phase where the vibration is incident on the plate, the path difference between the extraordinary and the ordinary component is equal to 0. The thickness D of the crystal is so chosen that when the two components come out of the crystal, they will be having a phase difference of pi. So this is the new direction of the ordinary component, and this is the direction of the extraordinary component. At phase 1, the electric vector was oriented like this, and when these waves come outside of the crystal, the direction of the electric field vector will be like this. So initially, the electric field vector was oriented like this at an angle theta. Now, when these waves come out of the crystal, these polarizations combine and the resultant electric field vector will be like this. That means that it has rotated by an angle 2 theta. Let us calculate the optical path difference and the phase difference in the case of a half wave plate as before. The optical path difference is given by NO minus NE multiplied by D equal to lambda by 2, from where we'll get the thickness as equal to lambda divided by 2 times NO minus NE. So in designing a half wave plate, we'll choose the thickness D in such a way that it is equal to lambda over 2 times NO minus NE. The corresponding phase difference, this is 2 pi over lambda multiplied by the path difference, and this will be equal to pi. Now let us summarize what we have learned when E ray and O ray overlap on each other after emerging from an anisotropic crystal plate. Remember that they cannot produce interference fringes as in double slit experiment because the direction of the polarization are different. Instead, they combine to produce different states of polarization depending upon their optical path difference. When the optical path difference is 0 or an even or odd multiple of lambda by 2, the resultant light wave will be linearly polarized. If the optical path difference is lambda by 4, the resultant wave will be elliptically polarized. In the particular instance, when the wave amplitudes are equal and the optical path difference is lambda by 4, the resultant wave is circularly polarized. These concepts can be used to produce and detect elliptically polarized, circular polarized, and linearly polarized vibrations.